Okay, in this video we're going to look at nuclear energy level diagrams in terms of gamma decays. So we're going to look at the processes behind what's happening in a gamma decay in terms of the energy. We know there's no physical changes in terms of the amount of nucleons, but we have said before that it's all to do with the energy of the nucleus and how that's changing. Okay, so the background here, gamma rays, we know that they are high frequency electromagnetic radiation, wavelength of approx 10 to the minus 11, and we know that gamma radiation is the byproduct of other decays. It doesn't affect the number or type of nucleons, but it occurs normally with or along with an alpha or a beta decay. And this is because the alpha or the beta decay can leave the new nucleus, often called the daughter nucleus, in what's known as an excited state. This additional energy is emitted as the nucleus de-excites. It emits the energy as a gamma ray, and this occurs only via certain quantum jumps until the nucleus has reached its ground energy state or its zero energy state. So because of this means that the gamma rays have specific characteristic wavelengths, and this may remind you of work that we've done in previously in year 12 to do with emission and absorption spectra. And all this is represented using nuclear energy level diagrams. So if we have a look at one, if we talk through this, so here we can see magnesium decays via beta emission to form aluminium in an excited state 1.02 mega electron volts above ground. So that's here, and what can happen now that the aluminium can de-excite by either emitting a 1.02 mega electron volt gamma photon, so all the way down to ground, or it can go via two levels, which is a 0.19 mega electron volt and then a 0.83 mega electron volt. So it can either emit one gamma photon or two gamma photons, all of different energies. So these will be different frequencies. Or what it can do, another method, it can decay via beta emission, forming aluminium in the excited state, but this time not in the 1.02. It can form it in the 0.83, and then of course it decays by the emission of a single 0.83 meg gamma photon. Using formulas that we've met previously in year 12, we could calculate the frequency of the most energetic photon emitted. Now the most energetic photon emitted here is the 1.02 mega electron volt, so that's dropping down from the 1.2 meg down to the 0 mega electron volt level. And using our formula of E equals HF, if we rearrange that to give us F equals E over H, and if we put in 1.02, 10 to the 6 is meg, multiply that by 1.6 times 10 to the minus 19 to give us an energy in joules. Remember, to convert electron volts to joules, you multiply by 1.6 times 10 to the minus 19, divide that by Planck's constant, and we end up with a frequency of 2.47 times 10 to the 20 hertz. So again, we'll just do another question. We'll talk through this. Cobalt 60 with 27 protons at an energy level of 2.81 mega electron volts. Okay, so there it is. Decays to nickel 60 by a beta emission. So here's the energy, here's the beta emission, and it's decayed to nickel 60. The beta particle and antineutrino only carry away 0.31 mega electron volts. So you can see this nickel nucleus is at 2.5 mega electron volts, a difference of 0.31 from the original 2.81. Sometimes this star notation means that it's in an excited state. So 2 stars means it's in a highly excited state. It then decays by gamma emission in 2 quantum jumps, the first being 1.17 mega electron volts to an excited state, then a final decay to its ground state. So here's the first 1.17, so 2.5 minus 1.17 will be 1.33, and I've now just got 1 star, 1 asterisk, to show that it's in less of an excited state, and then it can decay via a 1.33 gamma emission, mega electron volt gamma emission, down to its 0 state. So now it's just nickel 60 with no star. Draw an energy level diagram to show these transitions. Well, I've just talked you through that, and then calculate the frequencies of the 2 emitted gamma photons. So this first gamma photon here was a 1.17 mega electron volt. So if we just do the maths for that, using again E equals HF, if we rearrange it, F equals E over H, so it's 1.17 mega electron volts times 1.6 times 10 to the minus 19 to give us energy in joules, divide it by Planck's constant, and I get a frequency of 2.82 times 10 to the 20. And for this one, it's 1.33 down to 0. So again, using 1.33 times 10 to the 6 times 1.6 times 10 to the minus 19 divided by Planck's constant, 6.63 times 10 to the minus 34, gives us an answer of 3.21 times 10 to the 20 hertz. So these are the frequencies of the two photons as nickel 6D de-excites from its excited state down to ground.